Hi students, we are going to start our new chapter now, and that chapter name is heat transfer. So as the name indicates, we are starting with our new section in your syllabus, that is heat and thermodynamics. Heat and thermodynamics deals with what heat energy can make the changes, what changes heat energy can make in a system, or what is heat in a system and what is its effect in a system. So you know, as you already knowing what is heat. Heat is a total energy of all the particles present in the system, and average kinetic energy of the particles within the system is temperature. That means temperature is measure of heat energy. Temperature is the measure of heat energy. As heat is supplied to a system, its temperature rises. As you remove heat from a system, its temperature lowers. So how heat can be transferred from one system to another, or how heat can be transferred from one region to another region within a system, all these matters are discussed in this chapter, heat transfer. So as you already knowing, there are three methods of heat transfer. They are conduction, convection and radiation. Basic difference between all these three methods you are knowing, I think. Conduction is the process that generally found in solids. Convection is the process of heat transfer that you can found in fluids. Radiation is the mode of heat transfer which requires no medium. So that is the main difference between conduction, convection and radiation. So we are starting with the concept of conduction. So how conduction takes place, or what is the mechanism of conduction? See, as I already told you, conduction is happening in solid materials. That means whenever you are having, suppose you are having a steel rod, and this steel rod is heated by one end. Q amount of heat is supplied to this steel rod. So you know the temperature of this area, that is A and B, the surface area A and B. So that as the temperature, as the heat energy is supplied to the end A, its temperature rises. Its temperature rises. And if you are holding at the end B, initially you are not feeling at no hotness at the point B, and slowly you can find that the temperature of the end B is also increasing. But you are not directly heating at the end B, but you can find its temperature also increases as time goes. What is the reason for that? The reason is, as you increase or as you supply heat energy to the end A, from the end A, this heat energy can be transferred to the point B also. That means heat can be transferred from end A to end B. Through which method it is happening? That is the method of conduction. Through conduction, heat is transferred from the point A to point B. So what is conduction? That I already told you, the method of heat transfer found in solid materials. So what is the mechanism of conduction? What is the mechanism of conduction? When you consider one particle at this point A, when you consider one particle at this point A, solid particle at point A, as you heat it, its temperature rises. Its temperature rises. What is the temperature? Temperature is the average kinetic energy of that particle. Average kinetic energy of that particle. That means its temperature increases means its average kinetic energy also increases. Kinetic energy of that particle increases. But remember, it is a solid substance. So in solid substance, the particles are not free to move from their lattice points, but their energy, kinetic energy increases. So there should be some disturbance to that particle, but it can't move from its place. So what will happen? It starts to vibrate. It starts to vibrate. So as it vibrates, what will happen? It can collide with the neighboring particle. So through the collision, this energy, energy of this particle is transferred to the second one. Absorbing that, it starts to vibrate. Then it collides with the next one and transfers energy. Then set into vibration, and then it collides with another and transfers some amount of energy. Which means through successive collisions, through vibrations and successive collisions, heat energy is transferred from one point to another, one region to another through solid substance, through vibrations and successive collisions with the neighboring particles. So that is the method of conduction. That is the method of conduction. So conduction is the mode of heat transfer found in solid material. The mechanism is, as the high energy absorbed, the solid particle starts to vibrate, then it collides with the neighboring particles, and through successive vibrations and collisions, heat energy can be transferred from one point to another. So that is the process of conduction. See, when you consider the conduction, we can't say that heat energy supplied to the point A fully transferring to the opposite end. Heat energy supplied to the one end is fully transferred to the second end. Suppose Q amount of heat is given to the point A. Q amount of heat is given to the point A. From that, A amount of heat is absorbed by that cross-sectional area. Suppose we are heating this cross-section. So, through this area, A amount of heat is absorbed. Then, T amount of heat is, or we can say that in terms of heat energy only we can express it. Q1 amount of heat is absorbed. Then Q2 amount of heat is radiated out, or suppose through the surroundings the heat energy can be radiated out. So Q2 amount of heat is radiated out, and Q3 amount of heat is transferred to the next cross section. Q3 amount of heat is transferred to the next cross section. So we can say that the total amount of Q is equal to Q1 plus Q2 plus Q3. Q1 plus Q2 plus Q3. That means Q1 is the heat absorbed, Q2 is the radiated, and Q3 is transferred to the next cross-sectional area. So this is the total amount of heat energy. Total amount of heat energy given to a cross-sectional area. From that, some amount of heat is absorbed, and when the heat energy is absorbed by a cross-sectional area, its temperature rises. If it is not absorbing any amount of energy, means Q1 is absent. Q1 is absent means either the amount of heat energy given to a certain cross-sectional area, either it is transferred to the second cross-section, or some amount is radiating out. So no energy is carried by or absorbed by that particular cross section. Then what will happen? Then you can say that the temperature of that particular cross section remains constant. Temperature of particular cross section remains constant. So for suppose when you are heating continuously, we can say that cross sectional areas were not absorbing any amount of energy. That means Q1 remains constant, Q1 remains 0 throughout the cross sections. Which means, suppose this is A1 and this is A2 and this is A3 and A4 different cross sections. Suppose heat energy is transferred to A1. No amount of heat is absorbed, the amount supplied is transferred to A2. A2 is also not getting any or not absorbing any amount of energy, it is directly transferring to A3. A3 is also not getting any, taking any amount of energy. It is transferring for A4, which means no cross-sectional areas are absorbing heat energy, which means all the cross-sectional areas are kept at constant temperature. And that state is known as steady state of conduction. Steady state of conduction. At a steady state of conduction, no heat energy is absorbed by the cross sections. Heat energy given to that cross sectional area, particular cross sectional area, either absorbed or radiated out. Some amount of energy is transferred to the next, but no amount of energy is absorbed by the cross sections. So we can't say that all the cross sections are at the same temperature. If all the cross sections are at the same temperature, then no conduction happens. They are at different temperatures, but the temperatures remains constant. That means A1 is kept at temperature T1, A2 is at T2, A3 is T3, and A4 is T4, like that. That means temperature of each cross sectional area remains constant, but we can't say that all the cross sections are at the same temperature. Okay, so that is known as steady state of conduction. That is known as the steady state of conduction. Okay, so through during the conduction, we can have two situations. First one is steady state of conduction. Another is variable state of conduction. Variable state of conduction. What is variable state of conduction? Which means Q1, Q2, Q3 are present. That means heat energy supplied are absorbed by a part is absorbed, a part is transmitted, or a part is radiated. And in steady state of variation, from the heat energy supplied, there is no absorbed. Heat energy can be transmitted or radiated, not get absorbed. So that is the case of steady state of conduction and variable state of conduction. At the steady state of conduction, we can say that d theta by dt. What is d theta? Change in temperature with respect to change in time, which is equal to 0. That means when you are supplying heat into the situations in different cross sections, its temperature will not change with respect to time. That means it is not absorbing any amount of energy. That is why its temperature remains constant. So d theta by dt will become 0 at the steady state of conduction. D theta by dt will become 0 at the steady state of conduction. Okay. So in conduction, the factors affecting conduction are, suppose the same situation we are considering, A and B are kept at a distance L. So the amount of heat flowing proportional to from A to B, amount of heat flowing from A to B is proportional to area of cross section, and inversely proportional to the length, then directly proportional to the change in temperature between these phases, theta 2 minus theta 1. This is kept at the temperature theta 2, and this is at the temperature theta 1. So it will be theta 1 minus theta 2, theta 1 minus theta 2, because heat is flowing from high temperature region to lower temperature region. As you are heating here, obviously theta 1 will be high temperature and theta 2 will be at lower temperature. So Q proportional to A, proportional to theta 1 minus theta 2, inversely proportional to L, and obviously it is directly proportional to the time. That means amount of heat energy flowing from one point to another depends upon area of cross section through which heat is transferring, temperature difference between the points between where the heat transfer occurs, distance between these two, and time. So we can say that Q by T is equal to K into A into theta 1 minus theta 2 divided by L. Or you can take this theta 1 minus theta 2 divided by L together. That is change in temperature with respect to length. So that is temperature gradient. So that is K into, so theta by T is equal to, so Q by T. This is Q. Q by T is equal to K into A into d theta by dl. D theta by dl is temperature gradient. Temperature gradient. So amount of heat flowing. So rate of heat flowing. Rate of heat flowing is directly proportional to area and temperature gradient. Temperature gradient. So you can define K. So what is K? K is equal to Q by T into A into d theta by dl. So amount of heat flowing per second per unit cross sectional area between 2 points having unit temperature gradient. That is known as the thermal conductivity. That is known as the thermal conductivity. Thermal conductivity. So thermal conductivity is defined as amount of heat flowing per unit time. That is rate of heat flow per unit area of cross section between 2 points having okay, so thermal conductivity can be defined as rate of heat flowing per unit cross sectional area with unit temperature gradient between the points. So that is thermal conductivity. So thermal conductivity, coefficient of thermal conductivity or thermal conductivity, that we can define as the rate of heat flowing between 2 points per unit time with or through unit cross sectional area between 2 points having unit temperature gradient. Okay, so we can see whenever conduction happens, the amount of heat flowing is directly proportional to, or amount of heat flowing is depending upon our thermal conductivity also. Thermal conductivity of different materials are different. So whenever heat is flowing through different materials, the rate of heat flow through different materials will not be same. Thermal conductors are there, thermal insulators are there, and in thermal conductors also good conductors are there, bad conductors are there. So rate of heat flowing through different materials depending upon the nature of the material. Nature of the material means there are thermal conductivity also. So we can say whenever two conducting slabs are joined together, what will be the effective thermal conductivity? Okay, so for that you consider a conducting slab. Two conducting slabs are joined together in series. Two conducting slabs are joined together in series. Okay, so this is of conducting slab of length L1 with the conductivity K1 and cross sectional area A. Both are having the same cross sectional area, and these are the end points P and Q. See, this is another conductor of length L2 with thermal conductivity K2. Okay, so the point P is kept at a higher temperature theta1 and Q is kept at a, you can avoid this P and Q because Q is also we are taking the, so you can okay, you can take A and B itself. Two regions A and B, both are having the same cross sectional area, and end B is at a temperature theta 2, which is a lower temperature. So it is obvious that heat is flowing from higher temperature region to lower temperature region. For that, heat energy has to travel through two different conductors with their conductivities K1 and K2. So this is the point interface where they are joining together. So that region that is having at a temperature theta, that means interface temperature is taken as theta. We have to find out what is this interface temperature theta also. Okay, so we can say that whenever heat is flowing from A to B, heat crosses this junction, interface junction also. So the heat flowing through the first conductor, that is H1 equal to K1 into theta 1 minus theta 2 divided by L1 multiplied by H1 is there, no? So H1 is Q1 divided by T. So Q divided by T through the first conductor, we can take it as K1 into, obviously A will be there, Q1 into A into theta 1 minus theta divided by L1. Okay, K1 A into theta 1 minus theta divided by L1. And which is equal to K2 into theta minus theta 2 divided by L2 multiplied by A. Why it is so? Because heat is flowing from the point A to B. So the same amount of heat is flowing from A to B. Same amount of heat is flowing from A to B. So Q by T is same for both the conducting slabs. Q by T is same for both the conducting slabs. So we can say that H1 is equal to K1A into theta 1 minus theta divided by L1, which is equal to K2A into theta minus theta 2 divided by L2. Okay, so when you are comparing these two, we can say that A and A get cancels, and K1 by L1 into A and A get cancels from here. So K1 by L1 into theta 1 minus theta equal to K2 by L2 into theta minus theta 2. Okay, so theta terms you can club together. So it will become K1 by L1 theta 1 plus K2 by L2 theta 2 equal to K1 by L1 theta plus K2 by L2 theta. Okay, nothing we have done. This theta 2 you take to the left hand side, and this theta term you have taken to the right hand side. So we can say that this implies K1 by L1 plus K2 by L2 theta equal to K1 by L1 theta 1 plus K2 by L2 theta 2. Therefore, theta equal to K1 theta 1 by L1 plus K2 theta 2 by L2 divided by, you are cross multiply this one. So K1 L2 plus K2 L1 divided by L1 L2. Okay, you can cross multiply in the numerator also. So you can get it K1 theta 1 L2 plus K2 theta 2 L1 divided by K1 L2 plus K2 L1. L1 L2 is common, So they will cancel off. The remaining term will be k1 theta 1 L2 plus k2 theta 1 L1 divided by k1 L2 plus k2 L1. That is the interface temperature theta. That is the interface temperature theta. So we have now the interface temperature theta. Then you can go for H1. H1 is equal or H is equal to, because H1 and H2 are same because they are connected in series. So same amount of heat is flowing through both the conductors. So K1 by L1 into A multiplied by theta 1 minus theta. Theta is K1 theta 1 L2 plus K2 theta 2 L1 divided by K1 L2 plus K2 L1. Okay, so that is the temperature heat flowing H is equal to K1 A by L1 theta 1 minus theta. So you can cross multiply that. When you are taking that, you can take K1 by L1 into A multiplied by K1 theta 1 L2 plus K2 theta 1 L1 minus K1 theta 1 L2 in bracket. This is in bracket, no? So minus K2 theta 2 L1. In doubt? Okay, so K1 by L1 A into divided by K1 L2 plus K2 L1. So H will be K1 by L1 into A numerator and denominator. So from the numerator K1 theta 1 L2 minus K1 theta 1 L2 get cancels. So what is remaining there? The remaining terms are K1 by L1 into A multiplied by K2 theta 1 L1 minus K2 theta 2 L1 divided by K1 L2 plus K2 L1. K1 L2 plus K2 L1. So L1 is common, it can be cancelled. K1 A into K2 theta 1 minus K2 theta 2 divided by K1 L2 plus K2 L1. Hence, H is equal to K1 K2 theta 1 minus theta 2 into A divided by K1 L2 plus K2 L1. Okay, so K1 K2 into theta 1 minus theta 2 A divided by K1 L2 plus K2 L1. That is H. Okay, so the amount of heat flowing H is equal to K1 K2 A into theta 1 minus theta 2 A divided by K1 L2 plus K2 L1. So when you are rearranging that equation, you can write that equation as A into, this can be written as A into theta 1 minus theta 2 divided by L1 by K1 plus L2 by K2. Is there any doubt in that step? See, when you are cross multiplying the denominator, you can L1 K2 plus K1 L2 divided by K1 K2. That K1 K2 is going up. So you can write it as K1 K2 A into theta 1 minus theta 2 divided by L1 K2 plus L2 K1. So you can write that equation as H is equal to A into theta 1 minus theta 2 divided by L1 by K1 plus L2 by K2. Okay, so when you are having that, when you are considering that two slabs as a single one with a length L1 plus L2, with a length L1 plus L2, then you can have that conduction, heat flowing per unit time, H is equal to K into A into theta 1 minus theta 2 divided by L1 plus L2. Is it? Suppose I think you are numbering that diagram. We are having that total conducting slab, and this slab is made up of two pieces. Okay, so this is having L1, this is having L2, then K1 and K2. When you are considering this as a single slab, you can say that H is equal to K into A into theta 1 minus theta 2 divided by L1 plus L2 divided by L1 plus L2. So when you are considering that equation, here, comparing that equation here, you can write when this is H and this is also the same H, so A and A get cancels, theta 1 minus theta 2 and theta 1 minus theta 2 get cancels. So K by L1 plus L2, is equal to K1 K2 divided by, that is K by L1 plus L2 equal to K1 K2 divided by K1 L2 plus K2 L1. K1 K2 equal to, therefore K is equal to K1 K2 into L1 plus L2 divided by K1 L2 plus K2 L1. What is this K? This K is the thermal conductivity, effective thermal conductivity of the combination. So we can say that K is equal to effective thermal conductivity when conducting slabs are connected in parallel series. Then effective thermal conductivity K is equal to K1 K2 into L1 plus L2 divided by K1 L2 plus K2 L1. Suppose both are having the same length L, then L1 plus L2 will become 2L, and this will become L is common, K1 plus K2. So L and L get cancels, so that will become 2K1 K2 divided by K1 plus K2. If both are having the same length, then K is equal to 2K1 K2 divided by K1 plus K2. So when two conducting slabs of thermal conductivities K1 and K2 are connected joined in series, then their effective thermal conductivity will be K is equal to 2K1 K2 divided by K1 K plus K2, where K1 and K2 are thermal conductivity of those materials and they are having the same length. Okay, so that is the effective thermal conductivity when conducting slabs are connected in series. So remember, thermal conductivity is the amount of heat flowing per unit time through unit cross-sectional area between 2 points having unit temperature gradient. So different materials are having different thermal conductivities. So when different materials are connected in a series, the amount of heat flowing through both will be same, because from A to B, the points A to B, same current heat is flowing. So heat flowing per unit time, Q by T is equal to H, that will be K1 into A divided by L1 into theta 1 minus theta for the first conductor, then theta 1 minus theta 2 divided by L2 into K2. A will be the second. Comparing and following the steps, you will arrive at the effective thermal conductivity K is equal to 2K1 K2 divided by K1 plus K2. General equation is K1 K2 into L1 plus L2 divided by K1 into K1 L2 plus K2 L1. If both are having the same length, then the company equation shrinks to 2k1 k2 divided by k1 plus k2. So that's all for today, and we will meet in the next class.